This conference will now be recorded.
Hello everyone, today we are starting a new chapter which is coordination compounds. In D block elements, that is the last chapter we have covered. There we have already seen, have some idea about the transition elements that are present in the D block. And these type of compounds, that is coordination compounds, they are particularly observed for these transition elements. Okay, so that is why after finishing that chapter, we should discuss this one. Now the topics that we'll be covering in today's class is molecules or addition compounds. Then there will be some important terms that we use in coordination compounds. We'll also see what is the difference between double salt and coordination compounds. Then Werner experiment, different types of ligands, and obviously some related problems. Okay. So molecular or addition compound. Fine. Under this category, we have two types. One is double salt, another one is coordination or complex compound. But first, we have to know what is molecular or addition compound. So both these terms can be used and it has same meaning. So the concept of coordination compounds, it originates from the tendency for complex formation of transition element. So complex formation of transition element that we have already seen in case of D block elements, right? And why they have complex formation tendency, the reason behind that also we have seen. Now the question is, when solution of two or more simple stable compounds in molecular proportion are allowed to evaporate, then crystals of new substances are formed, and these compounds are known as, that is a newly formed substances, they are known as molecular compound or addition compound. So how we are getting it? We have taken solution of two or more than two, and all these are basically simple stable compounds, and we have taken them in molecular proportion, and then after taking this solution, that is the mixture of solution, we are allowing it to evaporate. So crystals will be formed. Now when you are getting back the crystals, now its nature, chemical nature is completely changed. Now we are getting some new kind of compounds, and that are known as molecular or addition compounds. Now two types possible. One is known as double salt or lattice compounds. Another one is coordination or complex compounds. So the second type is basically the main based on which this chapter is all about. But first we will see what is double salt. After that we will see what is coordination compounds, and obviously the difference between these two types. So double salt or lattice compound, mostly double salt, this term is used. There are some molecular or addition compounds which are stable only in solid state. So as long as it is in solid state, it will be stable. But when you are taking it in water medium, then the individual constituents will be obtained. Okay, so there will be it will be broken down into individual constituent, and this observation when we are seeing, that means it is double salt. We will take one example. Here we have two examples of double salt. One is potash alum, second one is more salt. So in potash alum, you can see we have K2SO4, aluminium sulfate, and some molecules of water. As we know, it is, we call it water molecules of crystallization, right? And more salt is ferrous sulfate, ammonium sulfate, 6 water. Now take any of these two. So here we have taken potash alum. Now when it is in solid form, this is the format by which we express it. But when you are dissolving it in water, now what will happen? All the constituent cations. So what type of cations here we have? K plus is present, aluminium 3 plus is present, sulfate is also present in both these salts. So all these cations and anions we are getting. See, that means when it is in water medium, this is in water medium, if you are doing some test, identification test for K plus, aluminium 3 plus or sulfate, you will get all these tests positive. Why? Because now individual constituents are present in the water medium. But when it is in solid state, then it is not the case. Now the formula is completely different. Fine. So this is all about double salt. Now the main difference with coordination compounds is that after dissolving in water, you will not get all these individual constituent as you are getting in case of double salt. So that is the main difference. Fine. So next we see what is coordination compound. So this is a second type under molecular or addition compound. Remember, this is a modern term used for this type of compounds, coordination, but sometimes complex compounds are also used. But we will, am I not audible? Am I audible? So coordination compounds, they are special class of compounds in which the metal atoms or ions, they are bound to a number of anions or neutral molecules. And these anions and neutral molecules, they are having some characteristic property. So that there is a central metal atom. Just look at this example. There is a central metal atom, chromium. Surrounding it, there are total 5 water molecules and 1 chlorine. And also 2 chlorine present. And gradually you will be understanding that what is the difference between these two types of chloride. Okay, there is difference. But the main important thing is here we have a central metal atom. It may be metal atom, that is zero oxidation state, or it may be carrying some positive charge. In that case, we will call it ion. Okay. Am I audible now? Am I audible? Am I audible?
Yes, ma'am.
Okay. So what I'm saying that there is a central metal atom. It may be neutral atom or it may be carrying some positive charge. In that case, you will call it ion. And some anions are surrounding it. So in this case, we have chloride ion and neutral molecules. For example, water is neutral molecule. So these are surrounding this metal. So modern terminology is coordination compounds. Now the difference with double salt is that when you are dissolving it in water medium, that is when it is in solution state, then they retain their identity in solid as well as in solution. Now see what happens. A part or whole compound of this compound is not dissociated in solution. So that is the reason its behavior is different from its constituent. Now see difference. We will take particular example. Okay, before going to that, here let's see all these examples. The first example, chromium, it is attached with 5 water molecules and 1 chlorine within this third bracket, and outside the third bracket it is mentioned chlorine 2Cl-. Now when it will dissociate, what will happen? You will get this type of cation, CrH2O5 Cl 2 plus and 2Cl-. So how I am writing it? Because this outside the third bracket, the 2 chloride ion that are present, that will be dissociating. but this total moiety which is present inside the third bracket, which is basically known as coordination sphere. Later we will discuss all these important terms. Right now I'm just using third bracket, not coordination sphere. So the moiety that is present within the third bracket, there will be no further dissociation. Okay, is it clear? Similarly, if you are taking K3FeCN6, what you will get? You will get 3 potassium ion, because potassium is now outside the third bracket, and you will get FeCN6 3 minus. And how I am writing the charge? Because there are total 3 potassium plus. That means total negative charge must be 3 negative, because overall the molecule is neutral, right? So in this way, we can write what will be the dissociation product. Now, if we take the last example, what we will get? We will get CO, 5 ammonia, then 3 carbon monoxide, sorry, it is carbonate, it is not. Carbonate and 1 Br. Now, 1 Br means single negative charge. So, positive charge must be single positive charge. So, this is the cation, this is the anion we are getting. Remember, whatever moiety we will have inside the third bracket, there will be no dissociation. And why there is no dissociation, we will come to that point later. Similarly, if we take FeCO5, see here we do not have any third bracket. That means if you are dissolving it, you will not get any cation or anion. Okay, and if you are dissolving this one, this will be the cationic part, and you will get 4 Br minus. Okay, so up to this point, is there any doubt that after dissolving it in water, you are not getting all the individual constituent? But if it is double salt, then we can get all the individual cation and anion. Fine, this is the main difference between these two. Now, here we have a question. The question is aqueous solution of K4FeCN6. So see, this compound is just like this one, only difference is here instead of K3 we have K4. That is the only difference. It is saying that aqueous solution of this compound does not give the taste of Fe2 plus cation, and it is also not poisonous like potassium cyanide. We know potassium cyanide is poisonous, right? Now, what is the reason behind it? K4FeCN6, when you are taking in aqueous medium, only you will get 4K plus. But this moiety, it will not be dissociated, it will remain like this. And as there are 4 positive charge, there will be 4 negative charge. Fine. So, Fe, though it is having oxidation state 2 plus, but it is not dissociated. It is remaining in the third bracket. So that is why it will not give the taste of Fe2 plus, because you do not have any free Fe2 plus ion. That is the reason you are not getting the taste of Fe2. And the second thing is, it is not poisonous like KCN. Now, if you want to get KCN, there must be presence of K plus as well as Cn minus. Then only you can get KCN. But Cn is inside the third bracket. Then how you will get free Cn minus ion? So that is why it is not poisonous like KCN. So the answer is, being a complex salt, it ionizes to K plus. There will be basically 4 K plus, and this ferrocyanide ion. Due to absence of Fe2 plus in free state, it doesn't give the taste of it. And also the absence of free Cn minus makes it non-poisonous. Okay, so the answer is clear for this question. But if you take KCN and if you are dissolving in water, obviously it will be poisonous. But here that is not the case. Now the main points for difference between these two. In solution, it dissociates completely. That we have seen in the previous slide. But for complex salt, it doesn't dissociate completely. It loses its complete identity, but it keeps intact some of its identity. So that is why it is mentioned, retain their identity. It gives a taste of all its constituents. Remember in the last slide what we have seen? Here from K2SO4, L2SO4, you are getting all these individual cations. So it will give positive test for K+, for Al3+, for sulfate. That point is mentioned in this table, the third point. It gives all the test positive for its constituent, but that is not the case for complex salt. And here we have one example. Okay. So these are the difference between these two. But our main focus in this chapter will be on the coordination compounds, not double salt. Now, next topic is Werner's experiment. Now, this experiment is important because this is the origin of this type of special type of compound. Because coordination compounds are completely different types of compounds, and their chemistry is also different types. So that is why there is a complete different chapter for this type of compound. But how these compounds are discovered, that is how it is originated. Now we will focus on it. Fine. So Alfred Werner, what he has done, he is the first person to formulate his ideas about the structures of this type of compounds. So what he has done in his experiment, in a series of compounds of cobalt chloride with ammonia. So there are some compounds of cobalt chloride with ammonia. So it looks like this. See, cobalt 3 chloride. That means if cobalt is having 3+ oxidation state, there must be 3 chloride to balance this charge with ammonia. So that is why ammonia is also mentioned. But ammonia number may vary. It is 6544. But Cl, it is always 3. Now, in a series of compounds of cobalt 3 chloride with ammonia, series of compounds, because we have taken total 4 types of compounds. And what it done, it was found that some of the chloride ions, because in each case there is 3 Cl minus, that is clear from the formula. But when we are adding AgNO3 to these compounds, AgNO3 means it is the source of Ag plus ion. And we know that if there is Cl minus ion in contact of Ag plus, it will form the precipitate of AgCl. Now, when you are adding AgNO3 solution, what happens? You are adding it excess. It is not that you are adding some particular amount, you are adding excess. Some of the chloride ions could be precipitated in the form of AgCl, but some remaining in solution. That means, look at this formula. The first one, COCl3 6NH2. Here we have total 3 Cl minus, and you are getting 3 moles of AgCl when you are adding AgNO3. So it is fine. It can be understood because there are total 3 Cl minus. But from the second one, now you are getting 2 moles of AgCl. But you should get 3 moles of Cl minus, right? But you are not getting so. You are getting only 2 moles of AgCl. And from this one, see the same compound, 2 different color. That means there must be some difference. But if you are writing this in this format, you will not be able to understand why these two are written different color. So just forget about the color. Look at this observation. From both compounds, you are getting 1 mole of AgCl. That means out of 3 Cl minus, only 1 Cl minus is precipitated. So from this observation, we will now derive the formula. Okay. So all these are traditional formula that is already written in the first book. And free Cl minus ion, how we will understand? From the moles of AgCl. So 3 moles of AgCl means 3 free Cl minus ion there. In the second case, you have 2 Cl free. Here 1 Cl free. This is also 1 Cl free. That means when the formula is like this, that is 3 Cl minus outside the third bracket, then you are getting 3 chloride. Okay, and that means free Cl minus, it is 3. Now total number of ions, here it is mentioned in the second column, 4. So why it is so? Because from this you will get this type of cation 3+, and you will get 3 anion. That means 1 cation, 3 anion. So total number of ion 4. Similarly, for the second one, you will get 1 cation, 2 anion. So it is 3. Then 1 cation, 1 anion. It is 2. But the last one, COCl3, 3 ammonia, though this formula is not present in the first box, but that is fine. COCl3, 3NH3. The formula, here we do not have any Cl outside the third bracket. So free Cl minus ion not present. And total number of ions is 0 because there will be no dissociation. Whatever moiety will be present inside the third bracket, there is no dissociation. Okay. And the last column, charge of the complex mentioned, that is, it is basically the charge of the cation. So when there are 3 anion, the charge of this moiety which is present in the third bracket, it will have 3 plus charge because 3 plus charge will be balanced by 3 Cl minus. Similarly, the second one, the cation will have 2 plus. Here it is 1 plus. The last one, there is no charge. Okay. So up to this, is there any doubt? Should I repeat any part? Now we will see the full structure. CONH3, 3 plus. So just focus on this. This is written here. Okay. So see here it is mentioned yellow color. That means cobalt, it is associated with 6 ammonia. So this is actually this compound, the first one. So 6 ammonia surrounding cobalt inside the third bracket, carrying 3 plus charge. So this 3 plus charge will be balanced by 3 Cl minus, which is written in this way. So this is orange yellow color. This is the cation. And the second one, when cobalt is having 5 ammonia and 3 chlorine. Now, as it is giving 2 moles of AgCl, that means outside the coordination sphere, there will be 2 chlorine. That is 2 chloride basically. So 1 chlorine will be inside. So see here also total 6 ligands are there. Here also 6 ligands, but 5 ammonia and 1 chlorine. So now this is the cation and it is purple color. This coordination compound. Okay, the second one, purple. Okay, any doubt? Now, if you are thinking that why the moiety which is present inside the third bracket, why it is not dissociating? Why only the outer part is dissociating? Now, the reason is here we have 2 different types of bonding. So, these 3 Cl minus that are attached with this third bracket moiety, it is actually ionic bond. Okay, but that is why it is dissociable. But all these bonds, these are actually coordinate bonds. Now, covalent bond, ionic bond, there are different types of bonding. So covalent bond means what? Suppose we have bond between A and B. Okay, one there is proper sharing of electron pair according to the definition of covalent bond. So 2 electrons are there. One is given by A, another one is given by B, and after that it is equally shared among them. And if it is ionic bond, what happens? A is completely giving electron, so that is why it is becoming positively charged, and B is completely accepting electron, so it is becoming negatively charged. Just take the example of NaCl. So now there is no electron sharing, but interaction, electrostatic interaction between positive and negative charge. So this is ionic bond, this is covalent bond. But what is coordinate bond? That is another type. Now try to understand the difference. When it is A and B and we have said it is covalent bond, one electron given by A, another one B. But suppose if the case is such that both the electrons are given by single element. So here both the electrons suppose given by B and A is now, that is after this donation of electron by B. Now they are equally sharing the electron. I am trying to say that after donation of this electron, they are just behaving like covalent bond. Don't think that they are behaving like ionic bond. No, there is no plus and minus charge. It is, in case of covalent bond, one is given by A, another one is given by B, and then there is equal sharing. Similar case is also in case of coordinate bond, but the difference is both the electron is coming from one side. So is it clear what is the difference between covalent bond, coordinate bond? So this type of bond is actually formed among all these. And here A is basically the metal and B is basically the ligands. Now these ligands, it may be neutral. So ammonia is example of neutral ligand. It is donating electron through its lone pair. But Cl is ionic. It is actually Cl minus. Okay, so different types of ligands may be there, neutral as well as ionic. But as there is coordinate bond present, so that is why it is not dissociable. Fine? Any doubt? So first two molecules we have seen, that is one is yellow, another one is purple. But now see why these two compounds, same formula, same traditional formula, but color is different. Now try to understand the reason. Here you are getting 1 mole AgCl, that means only one Cl is outside the sphere. That is why you are getting 1 mole AgCl. So 2 chloride inside the coordination sphere, or better I say third bracket. Now inside the sphere, these 2 chlorine, their environment may be different. See, in the green colored coordination compound, that is this one, the 2 chlorine, they are 90 degree to each other, and it is known as cis. Cis-trans terminology we use in different cases, right? For example, when there is alkene CC double bond, if both the same groups are on the same side, we say it is cis. But when it is octahedral arrangement, like 6 coordination is there, now the cis and trans, it is comparatively different. So when you will say cis, when the two same group or atom or ion, whatever it is, they are 90 degrees to each other. But if they are 180 degrees to each other, now it will be trans. So just because of this different in the arrangement, the color is different. So we cannot say they are same compound. They are actually isomer, right? So this is the violet one, that is the number 4. This is green. Okay, cis is green, trans is violet. So in this slide, any doubt? Should I repeat any part? Now the experiments we have seen. Next, what we will do, we will try to see what are the main postulates that are found from this experiment. So these are the main postulates of his theory. In coordination compounds, the central metal, it shows 2 types of linkage, or you can say 2 types of valency. One is primary valency, another one is secondary valency. Now, primary valency, they are basically the oxidation number and normally ionizable, satisfied by negative ions only. Because primary valence, if it is oxidation number, suppose oxidation number is +2 or +3. So this positive charge, it can be balanced only by anions. It cannot be balanced by some neutral molecule, right? Only anion can balance it. So the oxidation number, that is actually the primary valence, and it will always be satisfied by negatively charged ligands. And what about secondary valency? Secondary valencies are non-ionizable and are satisfied by neutral molecules or negative ions. Now, non-ionizable part, which one? Remember, The moiety that is present inside the third bracket, that is actually the non-ionizable. And here metal is associated with different number of ligands. It may be Ml6, it may be Ml4. So this number, that is actually the secondary valence. Fine. And these numbers, that is the ligands that are present inside the third bracket, it may be neutral molecule, it may be Cl. Example you have already seen in the previous slide, that sometimes inside the bracket there is ammonia as well as there is Cl. That means both neutral and ion, it may be present inside the coordination sphere. So secondary valency is equal to the coordination number, and it is fixed for a metal. Okay, that is a specific metal, their coordination number is always fixed. So remember, primary valency is all about oxidation number, that is the oxidation state, and secondary valency is nothing but the coordination. Sometimes what happens that some molecule will be given, that is coordination compound will be given, and it can be asked that find out its secondary valency and primary valency. Okay. The ion groups bounded by the secondary linkages to the metal, they will have characteristic spatial arrangement corresponding to their different number. It means the meaning of this statement is different spatial arrangement that are present in the secondary linkage. That means when it is 6, it will be octahedral. When it is 4, it may be tetrahedral or it may be squarehedral. Both possible, right? So different spatial arrangement corresponding to different numbers. Whether it is 4 or 6, these two numbers are mostly observed. So that is why I have mentioned only these two. So here we have example. So this molecule, if I write the molecule in this way, see there are total 5 ammonia, 1 Cl inside the third bracket, 2 Cl minus outside. So this is the primary valence or ionization sphere. Basically, this is coordination sphere, this moiety. So that is why the outside that is present, outside atom or group, that will be known as ionization sphere. And this number, that is all these 5 ammonia and 1 chlorine, they are primary as well as secondary valence. Why? Because here, see, this Cl, it is not only the secondary valency. Yes, it is true that it is secondary valency because it is part of coordination number. But see, this is also carrying some negative charge. This is actually Cl minus. So it is also satisfying the positive charge of cobalt. So here cobalt is 3+. Okay. This Cl, it is actually both primary valence as well as secondary valence. So that is why the arrow is towards this chlorine. Why it is both? First reason, it is satisfying the coordination, it is satisfying the that is balancing the oxidation state. That means it is 3+. So 1 Cl minus means now the charge will be 2+. And that 2+ will be balanced by 2 Cl minus. So now it is behaving as if it is primary valence. But this is also fulfilling the coordination number. That is, it is a part of coordination moiety. So now it is also secondary valence. So this ligand, it is primary as well as secondary valence. That is, it is fulfilling both the criteria. But the outside chloride, it is only primary valence. Okay. So is it clear? So this chlorine is primary valence as well as secondary, but this one is only primary. Any doubt? Any doubt in this slide? Next we have a question which is completely based on Werner theory. PtCl4 and ammonia may form 5 complexes. So see all these formulas, it is just like the formulas of cobalt complex you have seen in Werner's experiment, right? Total 5 compounds are there. A, PtCl4 6 ammonia. B, PtCl4 5 ammonia. C, PTCl for 4 ammonia, D PTCl for 3 ammonia. Gradually the number of ammonia is decreasing, and E is 2 ammonia. Total 5. Now 1 mole of each of these 5 you have taken, and you are adding excess of AgNO3. And what you are getting? You are getting 4, 3, 2 and 1 mole of AgCl respectively. Okay. While E gives no AgCl. That means 4 from A, from B 3, it is C, it is from D, and from E it is 0. So next statement is the conductances of their solution are in this order. On the basis of Werner's theory, you have to write their structure, and you also have to give the total number of ions given by these 5 complexes. That is, when you are dissolving in water, total number of cation and anion you have to add, and you have to write the number. Okay, the question is clear. First you have to understand the question properly. Once it is understood, then you can answer, right? So here the formulas, these formulas, it is already given in the question. Now in the second column, that is a structural formula, how we have written it, it is very easy to understand, because from A you have obtained 4 AgCl. That means 4 Cl minus must be present outside, and rest of the part means you have 6 ammonia left, because all the 4 chlorine outside. So that is why this is the formula. Then from B you are getting 3 moles of AgCl, so 3 Cl there, but 1 Cl will be inside, so that is why now the formula is like this. From C you are getting 2 moles of AgCl, so 2 chlorine will be inside and 4 ammonia is there. Then 1 mole AgCl, so that is why the formula. And for E you are not getting any AgCl, so outside the coordination sphere there is no Cl. So you have 2 ammonia and 4 Cl. This is the formula, right? So this is the structural formula. Now conductance order is given. On the basis of Werner's theory, you have to find total number of ions. Now conductance, it is directly proportional to number of ions. That means if it is maximum for A, so here number of ions maximum. For E, it is minimum. Okay. So even if this information is not given, that is, suppose the statement related to conductance is not given, then also you can easily answer the question. Because once you know the structural formula, you can easily write what will be the ionization, that is, after ionization, what will be the species you will obtain. Okay, so here you will get this cation and 4 Cl minus. So 1 plus 4, total 5 ions you will get. Then 1 cation 3, that means 1 plus 3, 4. 1 cation 2 anion, 1 plus 2. 1 cation 1 anion, 1 plus 1. Here ionization is not possible, so it is 0. So see, as we are moving from A to B to C to D, gradually the number of ions are decreasing, and that is why the conductance order is like this, because this is directly proportional to number of ions. Number of ions decreasing, conductance is also decreasing. Okay, the question is clear. Now different terminologies. Here we have this compound, cobalt 6 ammonia 3 plus charge. Okay, central atom, the first term, central atom or ion. Now this is central metal atom or ion. In this case it is written ion. Why it is written ion? Because it is having oxidation state 3 plus. How you are understanding that oxidation state is 3 plus? Because outside third bracket it is mentioned 3 plus. Ammonia has no contribution for charge because it is neutral. So whatever charge is mentioned outside the coordination sphere, That will be directly on the cobalt. Okay. So it is carrying some charge, so that is why it is ion. But suppose if it is neutral, for example, FeCO5, 5 carbonyl ligand attached to Fe. Now carbonyl is neutral and overall the molecule is also neutral. That means here oxidation state of iron is 0. So in this case, you will use the term central atom, not ion. But if it is carrying some charge, you have to call central metal ion. The atoms and ions to which a set of number of atoms, molecules, or ions are bound are referred to as the central atoms or central ion. So sometimes a set of atoms may be attached, sometimes molecules may be attached, suppose ammonia, water, or carbon monoxide. Sometimes ions may be attached, for example Br minus, Cl minus, like this. Here the central atom or ions are typically acting as Lewis acid. Why? Because it is accepting electron pair from ligands. So you can call them as if they are electron pair acceptor. Okay. Next terminology, coordination number. Though we have already discussed about it. So the number of total moiety, the number of total atoms or groups or ions that are attached to the central metal atom, that is actually the coordination number. Total number of donor atoms of ligands to which the central metal ion or atom is directly bonded, that is known as coordination number or coordinate number of that particular atom or ion. So it is, you can also say from other point of view as if it is a number of coordinate covalent bond. Coordinate covalent bond is basically coordinate bond. Sometimes it is mentioned in this way, coordinate covalent bond. You can simply write it as coordinate. Okay. Which the ligands form with the central metal ion or atom. So the light transition metals, that is the first transition metals, the first series. Remember, in D block we have first series, then second transition series, third transition series. So here if we consider the first transition series, mostly you will see these two coordination numbers are common. But if it is heavy transition metals, for example platinum, palladium, they can even exhibit, not even platinum and palladium, you can also consider some other metals, because when size is very high, coordination number can be easily increased, because now the space around the metal atom or ion, that is also increasing because of their larger size. So now it can accommodate higher number of ligands surrounding it. Okay. Third term is ligand. Now ligands are these molecules, or it may be Cl minus ion. So it may be atoms, it may be molecules or ions which form coordinate bonds with the central metal atom or ion by donating electron pair. Okay. So now you can say central metal atom, if it is behaving as Lewis acid, so obviously ligands are behaving as Lewis base. Lewis base definition is electron pair donor. Okay. So as if coordination compounds are Lewis acid Lewis base interaction. That is also we can say that for this type of compounds. Okay. The fourth term, coordination sphere. So this is the non-ionizable part of a complex compound. And what it consists of? It consists of central transition metal ion surrounded by neighboring atoms or groups, and it is denoted by a square bracket and collectively called as coordination sphere. So this is the coordination sphere, this total moiety inside third bracket. Fine. Counter ion. What is counter ion? This is the ionizable part of complex compound. That means whatever moiety is present outside the coordination sphere. So suppose there is presence of sulfate or Br or Cl or A. So this is counter ion. So this is the ionizable part written outside the bracket. Fine. Next term, coordination polyhedra. It is actually the geometric shape formed by the attachment of the ligands to the coordination center. So suppose if there are 6 atoms or ligands, it is having octahedral arrangement. If it is 4, that is a special arrangement. If it is 4, it may be square planar or it may be tetrahedral. Both are possible. Okay. Oxidation number. The actual charge that a metal atom experiences in a complex, that is the oxidation number or oxidation state. How you can calculate it? By finding the charge associated with it when all the electron pairs that are donated by the ligands are removed. So for example, suppose you have PtCl6 2-. Here you have to find out oxidation number of Pt. How you will do it? Suppose it is X. So X plus 6 into -1, because we have total 6 Cl minus. Overall charge is 2-. So this type of equation you have to write first, then X you can easily find out. So it will be 6 minus 2 plus 4. So plus 4 is the oxidation state of platinum. Okay. Any doubt in any of these terminologies? The last term that we have mentioned, oxidation number, and we will now find out the oxidation number of the central metals in these entities. Total we have A, B, C, D, E, 5. So for cobalt, here we have cyanoligand, which is carrying -1 charge. Water, it is neutral. And En. What is En? En is this one. H2N, CH2, CH2, NH2. So this is a bidentate ligand. It can bond from both sides. But remember, it is neutral. You can consider it as if it is derivative of ammonia. If you replace one hydrogen of ammonia with CH2, CH2, NH2 moiety, you will get this ligand, right? So this is also neutral. Now, if it is -1 charge and outside we have 2+, that means X, which is the oxidation number for cobalt, plus -1 for cyano, total charge 2+. So X will be +3, 1 plus 2. Okay. Then for PtCl for 2-, we have already, no, it is different, sorry. We'll do it once again. It is X, so X plus 4 into -1 -2. So it is +2. Okay. Then for C, again X, 3Cl-. So X plus -3 into, sorry, it is actually -3. Ammonia is neutral. Overall there is no charge, so it is 0. That means X is +3. Okay. So more you will practice, you will see that even you don't have to do all these calculations. So don't have to waste time in doing all these calculations. Just looking at the complex, you can easily understand what will be the oxidation number. Because see, just take the third example. Ammonia is neutral. Fine. 3Cl is there. Each is carrying -1 charge. That means total it is -3. So obviously the positive charge will be +3, which is the oxidation number for chromium. Okay. Then we have cobalt 2 bromine and En, ethylene diamine again. Now it is X, but we will not do the calculation. Just try to see. Outside we have 1 positive charge, and for Br2 we have 2 negative charge. That means even after presence of -2 charge, there is still 1 more positive charge left. That means cobalt is having oxidation number +3, right? So without writing the equation also, you can find it out. And here we have 2 potassium ion. That means outside the charge, actually only in the last one, here we have some counter ion. Because in other examples, if we see, directly the charge outside the coordination sphere is mentioned. But in the last example, no charge mentioned, but it is 2 potassium present. That means if you focus only on this part, there will be total charge 2 negative. Now there is 2 negative charge, and we know 6N means 6 negative charge. So 2 negative charge extra when there is some positive charge and -6. That means it must be plus 2. Sorry, it is actually K3. It is not K2. Because if it is K2, then we are getting oxidation number 4 for Fe, which is not possible. So it is basically formula is K3 FeCN6. Outside there is total 3 negative charge, and oxidation state is Fe3 plus. So 3 plus charge, then 6 negative. So 3 negative charge will be extra, which is present outside the sphere, and that will be balanced by 3 potassium. Okay. So all these 5 examples are clear. Classification of ligand. Now we know what is the term meaning of the term ligand, but there is some classification we will do for the ligands. But remember, this classification can be done based on different points. Okay. So for first classification is on the basis of charge of ligand, whether it is carrying negative charge or positive charge or carrying no charge. So when it is on the basis of charge, first category we have anionic ligand. So from the name you can understand it will be carrying some negative charge. And this is the most common type of ligand. All these are examples. Some examples you have already seen. Some more examples also we have. It is sulfite ion, sulfide ion, sulfate ion. Okay, hydroxy ion. Then neutral ligand. Now neutral ligand example also we have already seen. They are uncharged. And how they will donate electron? They will donate electron not through negative charge but through electron pair. Here in H2 we have lone pair over oxygen, lone pair over nitrogen. This is 3-degree amine, this is carbonyl. Here also we have lone pair. Okay, and there is a rare category which is not very common. Actually, it is not common at all, and that is cationic ligand. Now there is one particular good example under this category, which is nitrosyl, NO plus. Fine. The next on the basis of denticity. Now what is denticity? Denticity is through how many atoms it is connecting with metal. Okay, so number of coordinating group present in a ligand, that is the denticity. Now until now all the examples that you have seen, mostly it is monodentate. Okay, but that is not the limitation. There are other examples also. So see, these are unidentate or monodentate. So from the term you can understand only one donating atom is there, nitrogen, Cl and oxygen. But some more possibilities are, see, bidentate. One example we have already seen, which is ethylene diamine En, which is NH2, CH2, CH2, NH2. So both the nitrogen can donate simultaneously to the metal. Okay, so see, here one molecule of En is satisfying 2 coordination site. Fine. So if any metal, when it is monodentate ligand, it will be Ml6. But suppose if it is bidentate ligand, and bidentate ligand, suppose if it is En, then to fulfill these 6 coordination site, basically 3 ethylene diamine is enough, because per En you are getting 2 donating site. Okay, so this is one example that we have already seen. Some more example, oxalate ion. In short, it is mentioned OX. Here I am writing this ion. So it is coming from oxalic acid. Oxalic acid formula, CO2 is CO2H. But if you remove the 2 hydrogen, it will be carrying 2 negative charge. So from both sides, it can donate electron to the metal. Then we have 110 phenanthroline. In short, it is known as PHEN. Now it is not carrying any negative charge. It is neutral. But there are 2 nitrogen atoms, fine, present in phenanthrin moiety. So that is why the name 110 phenanthroline. These 2 positions are actually 110. That is why the name is like this. Then glycinate. Now the simplest amino acid we know, NH2CH2CO2H, right? But suppose instead of writing CO2H, if I am writing CO2 minus, Now these two can be donating center. So one side you have neutral nitrogen, another side you have anionic oxygen, and this is glycinate. When it is neutral, that is, if you are writing it in CO2H form, the name will be glycine. But when you have removed H and you are now having O minus, now the term will be glycinate. In short, GLY. Then 2,2-bipyridine. Pyridine moiety is this one. But suppose another pyridine is attached to the ortho position and it is behaving as bidentate ligand. In short, it is di-PY. And carbonate, we write it in this way. But if you write the full structure, it is like this. So two donating site. Fine. So all these 6 examples of bidentate ligands. Is there any doubt? Should I repeat? Polydentate ligand, that means more than 2 donating site will be there. And under this category, we have basically tridentate, then tetradentate, and hexadentate. And detailed discussion, it will take time, so I'll discuss it in the next class. So until now, that is up to this slide. If you have regarding all the slides basically in the class, any doubt, please mention. So we are ending the session here. Thank you for listening.